Thank you. Hello, everyone. Thank you for your patience. We'll start in a minute or two. Okay, I think we can start. I want to thank the people behind the screens for making this happen. It's not trivial to make all the mics work, all projectors, everything. So highly appreciated the team behind the scenes. Thank you all for coming. I have extreme honor and pleasure to host and moderate this panel with my esteemed colleagues. And I want to point out how diverse team this is, diverse in different aspects of technology, gender, countries of origin, et cetera, et cetera. So from my left, we have Wen-Mei Hu, Norm Jouppi, Hironori Kasahara, Yale Patt, Guri, Sohi, and Carole-Jean. I would like to ask each of the panelists to introduce themselves. I'll just give an example. My name is Dejan Milojicic. I work at Hewlett Packard Labs in California. My area of expertise is operating systems, those guys that Yale just asked to help and will help. And with that, the next is Wen-Mei.
Hi, my name is Wen-Mei Hu. I was a former faculty member at the University of Illinois. I'm now at NVIDIA. I'm responsible for the systems research at NVIDIA.
I'm Norm Jouppi, and I've been at Google for the last 11 years and came to Google to start the TPU program and been working on that ever since.
Thank you. I'm Hironori Kasahara, Waseda University. I'm working at ISCA'25 General Co-Chair. My research topic is the co-design of a compiler and architecture. Thank you very much. So, Yale, please.
Yale, would you like to introduce yourself one more time, or you think you are well known at this audience?
Right now? Okay. So you can hear me? Yes? Okay, so my name is Yale Patt. I'm a teacher at the University of Texas at Austin, and teaching is what I love most, but research is also an important part of my life. I've been worrying about various characteristics and problems with instruction level parallelism for the last 50 years, and have had some success with out-of-order execution and branch prediction. And that's about all I have to say.
My name is Guri Sohi. I've been a faculty member at the University of Wisconsin-Madison almost 40 years, and I've been working on processor microarchitecture since then.
Hi, my name is Carole-Jean. I'm currently at AI Research at Meta Platform. I lead the ML system research. Prior to Meta, I was on the faculty of Arizona State University. Thanks.
So we will organize this panel in a way that everyone will give their statement of about 2 minutes, and I'd like to start in the reverse order that we just had. So I'll ask Carole Vu to make a statement of about 2 minutes.
Cool. So when Dejan invited me to serve on this panel, I thought about what data I can bring to share with the community. And this is some of the recent work that we have published at HPCA 2025. If we were looking at large model training, we collected a year worth of data, all the training jobs that's running on state-of-the-art training cluster, and try to understand, draw some insights from these real deployment data. On the right-hand side, this pie chart is based on all the training jobs that's running on this state-of-the-art training clusters with an attempt to understand when job finishes and how often do they fail. And it turns out that among all the jobs that's running on the training cluster within the year, about 60% of them finished, and a large percentage of them failed for various different reasons, which we'll talk about. And a small percentage of those job failures is coming from hardware, which this community focuses on. and that is 0.2%. What is interesting here is while hardware failure is rare, they can cause a lot of churns at scale. So the pie chart on the left-hand side is showing that 19% of the total training time is wasted because of these 0.2% of hardware failure. Next, please. So we take a step further to understand what are actually the causes for these hardware failures. And the figure on the left-hand side is showing where these hardware failures can come from. They can come from just unattributed costs, and it can come from file system mounts, it can come from InfiniBand links, that's the networking part of it, it can come from PCIe, ECC memories, and all the way to sometimes GPU cannot be detected, right? More detail is in our HPCA paper. What's also interesting to highlight is that failure rates can fluctuate over nodes and also over time. And so this is what makes these training reliability a really hard problem at scale. Next, please. On top of that, I guess we hear the keynote from Yale that talks about efficiency, performance, and all of that. And somewhere there, he talks about operational versus embodied carbon. So let's dive deeper into this particular characterization results that we have presented in HPCA 2021 paper called Chasing Carbon. This work is in collaboration with colleagues at Meta, at Arizona State, and Harvard University. We went through many sustainability reports that has been published by Apple, and we showed that among all the Apple devices, about 80% of Apple devices' carbon footprint is coming from manufacturing. Among those 80%, or 74% to be precise, among the 74% of manufacturing emissions, 33% is coming from manufacturing of hardware systems. So for example, the application processors, the memory, and the NAND flash storage devices. Only about 19% is coming from product use. So that's a story about battery-operated smartphone devices. Next, please. If we look forward, in the next generation of computing devices that computing industry is designing and producing, today we already have Ray-Ban glasses, these wearables that come with a wide variety of accelerator arrays. It comes with high-quality display technologies. If we are wildly successful, these devices will be used and deployed at the billion scale. So we expect the carbon characterization or profile to look quite similar to what we just looked at with these Apple devices. So this is a really good time to start thinking about, given the carbon characterization profile, how should we think about designing computer systems with that in mind?
Thank you, Carol. Guri, that was virtual 2 minutes.
Yeah, so I do not work in sustainable computing, but when I first started listening to talks on this, typically they are from the big companies, the hyperscalers as we call it, and most of them are either trying to, just in my view, mislead about the issues. So, when I first started listening to some of these talks, they would talk about the low carbon footprint of the data centers in France, without ever saying that the reason for that is nuclear energy, because no one wants to admit that's the way to get nuclear energy, that's the way to get low carbon footprint. Finally, we admitted to that, they're coming around to that. More recently, there's this whole talk about embedded carbon versus operational carbon. Again, in my view, a way of saying someone else is the problem, not our use of computing in these big AI data centers are the problem. So the first thing you have to do, actually, if you want to solve the problem, is to accept that you are part of what's causing the problem and then try and go and deal with it. And so the biggest, and then, a lot of the others, we are interested in computer architecture. do we have anything to do and a role to play as opposed to someone manufacturing it or building some chassis somewhere or building the bricks for the building? Okay, and if we accept that we have something to do with it, then really the main thing we have to worry about is energy efficiency. And how do we get energy efficiency in all aspects of the problem? And during a question and answer session, I think as we ask more questions, I'll try and elaborate more on that.
Thank you, Guri. Yale?
Yeah, I wasn't going to speak since I've already done too much talking today, but Guri pointed out something that I had inadvertently left out of my talk. I gave you a bunch of bullets, and the bullets were to highlight how you can save energy, but I didn't hammer home the next step, which is what you can do about it. So what you can do about it, Guri says we're all part of the problem. That's absolutely correct. We are all part of the problem. And what we need to do is look at what we're doing, and is there something about what we're doing that we can do differently that could result in a power energy savings. And that's the one point that I left out because of the jet lag, which is my problem, not yours. But anything further than that, I think I'll save for the questions and answers.
Thank you very much, Yale. Hironori?
Thank you very much. So I have a problem in English, so I will use a slide. This is different. Okay, thank you. So for sustainable computing architectures, thinking about the future, currently we have one data center, have nuclear reactors, and soon that will be changing to the one data center need two reactors, three reactors. But this kind of future is not sustainable. Maybe a kind of dead end. So consuming much energy and getting performance will be a kind of a corner of the computing. So I believed we should reduce the power consumption by using a different approach. So my approach is a compiler and hardware co-design. Design the compiler and design hardware to support the compiler optimization. And we have been researching on parallelizing compilers, memory optimization, like last level cache optimization for total program, and distributed shared memory optimization, and local memory optimization for embedded systems. And after parallelization, we are putting the power control. Please go to the next slide. Okay, thank you very much. And about 20 years ago, I organized a Japanese national project for power lowering, and developed 3 chips. First year 4-core multi-core, and next year 8-core homogeneous, and next year 15-core heterogeneous, having the 3 different accelerators, including DRP and dynamic reconfigurable processors. And compiler controls the power. Right over the curve showing the homogeneous multi-cores, just only compiler optimization, power reduced from 5.7 to 1.5. And the heterogeneous multi-cores, also power reduced 1.7 to 0.54. Why what is we are trying to create non-cooling required processor. Please. And this is an example of a compiler-generated schedule. And compiler check macro task 2, 6, 8 on a critical path. And the critical path is executed by 100% frequency. But the other part, we can put the lower frequency, and the compiler understands parallelism 2. Parallelism is 3, and we have 4 cores. We stopped 1 core power gating. And also heterogeneous multi-core, the same thing. So I think the one approach is a compiler, hardware, co-design, and the power reduction. Thank you very much.
Thank you, Hironori. Norm?
Hi. So I actually looked at the questions that Dejan sent out ahead of time, and I decided to give quick answers that we can elaborate on, or everyone can disagree with me on later. So what are the critical limitations of today's systems for the future? I think one of the big things is models are in a state of flux. And just in the last year, we've gotten much better results with much smaller models. So I think the biggest factor is going to be better ML models. But software in general, how we use the systems, power, obviously a big thing, and interconnect, I think, is one of those things that the community has it kind of left to supercomputing maybe or something for years, but I think it'd be great if there was more interconnect work at this conference. How are emerging apps different? What kind of support do they need? I think one of the biggest things about the new applications is that there's in ML and AI are they're very different. Some are interconnect bound, some are memory capacity bound, some are memory bandwidth bound, some are compute bound. So the key thing is that you can't hyper specialize because you don't know what the models are going to be, and you don't know like which ones are going to be the most popular. So you have to build a well-balanced machine. Let's see. I'm going to have to take my glasses off, sorry. What are the most critical innovations needed to overcome the limitations? I think co-design is something that's the most critical. And I know like Ph.D. programs, and in order to get tenure, you have to specialize in a certain area. But I think a really good model is what Berkeley used to do, where Dave Patterson got 5 professors in different areas. They could all work on sub-problems, but they would come together as a whole to make a bigger contribution. And I'd like to encourage more of that kind of work between professors either at the same university or different universities. Who will deliver innovation, academia, industry, community, or government? The answer is yes. So it's all of those, but they need to work across the stack. Hopefully via these the multiple collaborations, not only between professors at academia, but different organizations. And then finally, any advice for young computer architects? My biggest advice is to learn more about implementation constraints, because if you assume something that's very unlikely to be possible and then do your research around that, the impact of your research is going to be probably not as good as if you base it on real technology trends.
Thank you, Norm. We'll go through all these questions in more detail next as well.
Oh, okay, sorry.
Yeah. No, it's okay. Wen-Mei? No, it was a good summary. Thank you.
Okay. I think computer architecture is at this probably one of the best opportunistic times in the history now. We're making several assumptions that we have been making about the system has changed. Remember when neural networks was a kind of a fairy tale in the 1980s, and then they eventually faded, but it became reality in 2012 when the GPUs became capable of training neural networks. The assumption that changed was that the computational power was improved by more than 1,000 times, right? So today, what changed? What changed today is that the storage media, meaning the solid-state drives and the network devices and so on, are fundamentally different than when the operating system was first developed 50 years ago. So in the old days, we assumed that these things are going to take forever. And then we use the operating system whose services will take a long, long time, but it doesn't matter. But today, when we access the solid-state disks, when we access the network, things change. Things are now at the millisecond level and at the gigabyte speed. Things have improved by more than 1,000 times now. what happens in the next, if we look at the trend, is that the services that are running on the CPUs are no longer able to keep up. And I believe some of my colleagues at Google and Meta will tell you the same thing. The GPUs are not fed properly today, and things are not running as fast as they need to. And there are a few things that we are going to see, for example, the reliability problem. The problem is that we access other GPUs' memory through NVLink. We assume that it's as reliable as the memory interface. It's not. Every time there's a glitch, the whole system goes down. So we need to rethink about how we access things in the system, how we organize the system software, when the system software need to be out of the way, when APIs need to replace the traditional hardware functions. And these things are going to be the opportunities for all the students here and the faculty here. And I believe that we're going to see great innovations.
Thank you very much, Wen-Mei and everybody else. So here is how we're going to spend the remaining approximately 1 hour of the time. We went through the first part. Each panelist have approximately 2 minutes, and we heard your statements. I'll have a few questions that I will ask them. You can rotate, or you can pass if you, not everyone has to answer every question. And then we'll leave approximately 1/4 of the time for the audience to ask the questions. So the first question is, what are critical limitations of today's systems for the future? And Wen-Mei made amazing segue to that. Norm emphasized some, and then the other esteemed panelists have equally done so. Who would like to spend a little bit more detail on this question? Go ahead, Guri.
So, to me, actually, is it a critical limitation or not? It is really what seems to be the approach everyone seems to be taking is more, big. And Norm said, okay, now, you're finally gone down to some of the smaller models are better. So is it a critical limitation of a system or more of the ecosystem? The critical limitation I see is a little, you're not thinking about how to do things differently. And there are so many opportunities for doing things differently, I believe. And that is going, so the critical limitation, just keep going down the path that you have been going down. For more, just building more and bigger is not the right way.
It's the easy way.
It is the easy way, but it's not the right way.
You're absolutely right. It's the easy way, and people are lazy, and they want to get their interesting problem solved, and they don't want to waste any time on something that doesn't directly affect them today.
It's much easier to speak without microphone, but...
So I need the microphone, okay. Yes. So I'm saying it's the easy way. It's not the best way. You're absolutely right. But most people don't want to pay attention to the best way. They want to pay attention. So the best way is a global issue, and they are focusing on their local issue, and the global problem be damned. And I think that is the battle we have to fight, and we better do it soon. And you're right. There's too many things that we're doing wrong if we care about the global problem rather than solving my personal problem. So that's my 2 cents.
Is there anyone who disagrees with Yale Patt? Go ahead.
Oh, absolutely not. He's the one who signed my thesis. So, I think I just add to what Yale is saying. Let me just give one example about this. Recently, we have some issues with the NVIDIA Collective Communication Library. And one of the things that caused the problem is that it's a communicator-based approach based on MPI. And we always assume that in a large-scale system, we need to set up all the communicators and what they call the world, and then we have everything communicate with each other. And we also assume that the CPU has to be the one that manages the communication, so the CPU would launch a GPU kernel for each of these communications. Neither assumptions were true, so what happened is that when we have 100,000 GPUs operating, well, one of them is going to have trouble, and then the communicator breaks, and then the whole system goes down. And then we see some of the numbers that Carole-Jean just presented. Can that be changed? Yes. So we can do more of a dynamic connection, and the old assumption is that if you do dynamic connection, it's going to be too much overhead. The trouble is that CPUs are running so slow that you already have huge amount of overhead anyway. So internally, we already changed all that. So this is what I was talking about. There are limitations in the system that was based on the assumptions that were established many, many years ago. And these things are no longer true, especially when you have hundreds of thousands of computing devices deployed in these data centers. I think there's great opportunity for ISCA papers in the next decade to fundamentally change these assumptions and come up with the right solutions.
Wen-Mei is one of the best motivators I've ever met. So thanks for motivating the community. Any other, Carole?
Yeah, plus one to what Wen-Mei just shared. I do think that thinking about how to make our software systems to be more scalable, fault tolerant, and reliable is where this community can contribute to. But also on top of that, I guess with the carbon characterization results that I share, I do think that computer architecture community is well positioned to think about how to design systems with this reducing total carbon footprint in mind. So when we start looking at the bigger picture, the total life cycle emissions of a computer systems, how should we think about designing computer systems with that carbon cost? Can we do that on top of meeting the performance target, meeting the power efficiency requirements, and then on top of that, reducing the carbon cost of the systems that we bring?
Okay, Hironori?
Yeah, so Wen-Mei, you think that it's not what I said, but rather a lack of information as to what is really important, and that's why they're not solving the problem. I'm sorry?
Wait, I didn't say that you didn't solve the problem.
I didn't get that.
So what did I say again?
Okay, so what I got from your comment was that not that there's a problem of laziness or whatever, but rather that they don't know what the real problem is, and so they are, if they would be informed as to what the real problem is, they would jump on the bandwagon.
Exactly right.
Is that your point?
Yeah, exactly right. I think the tendency is to assume that if we have done this for 50 years, it has to be right.
So there's no question in my mind that we are focusing on the wrong problem. Yeah. I hope that I picked up a few things in my talk, but that's neither here nor there. It seems to me that if what you say is correct, that's solvable. It's just an education question, right?
Exactly right. So let me take the TLB problem, right? You mentioned the TLB problem for accessing a large data set, and there are too many pages and too many entries. The fundamental problem is when you access a big enough data set, do you really need to have a TLB hit in a small number of cycles, let's say 1 clock cycle? Do you really need it, right? And which application really need that short latency? Chances are, if you access a gigabyte out of a petabyte data set, some of them will have to come from somewhere else. Does it even matter if some of them have a 1 cycle hit latency, right? And we're cornering ourselves into some of these things because of the assumption that the 1 cycle TLB miss or hit is a great thing to have. But it may be a great thing to have for certain kind of data, but not all the data.
So revisit some previous virtual memory models.
I just want to jump in and point out that TPUs don't have virtual memory, so we don't have any problems with TLBs.
Hironori, you wanted to say something.
So, different. So, I think the critical limitation, I said before the power, again power, but before I talked about the high performance data centers, but I'd like to mention about embedded processors. So I worked with automotive companies and the real-time controller, and I think currently autonomous automobiles should use water cooling. But in my experience in the high-performance computing, when we use water cooling, many times water leaked. The floor of a high-performance computing center was a lot of waters. It means when we designed 100% no leak, but no 100%. So if we think about water-cooled automotive controllers, so the road is bumpy and the joint is sometimes have a problem, and if water leaks, drivers will die. So I think embedded systems power is very critical. That's why I'm saying that natural cooling processor is required for embedded.
Okay, great discussion. Let's move on to the next question so we can have some time for audience. How are emerging applications different? What kind of support do they need compared to the previous applications? And we can talk about elephants in the room, Yale, or any other applications you prefer. Who would like to tackle this question? Go ahead, Guri.
So I know nothing about emerging applications, but this is an opportune moment to say what I think might be happening in the future. So something to work about. So you know, to set it up, so if you take a look at the GPUs and doing all the training models, and I don't know much about GPUs, I know these things exist. Okay, so they used to do. Typically it started out with 64-bit floating point, right? Okay. And then they said, no, let's do 32-bit floating point. And the AI model, 16-bit floating point. And now we are down to 8-bit floating point. Why so? Because you can do more of those 8-bit floating point operations than you could do in the same space. Now, if you take a look at it, you're doing all these matrix multiplications and getting a n-bit value. With 8-bit floating point, you're getting an 8-bit value. You're doing millions and millions of multiplications to get the same value. Okay, and there are 3 dominant values when you do all this stuff. Okay, so the opportunities are going to be how to do these things in a much more efficient manner, rather than keeping on repeating the computation again and again. Now you do your training with whatever you do, you're doing these inference on whatever, I don't know, 8 16-bit values. New inference coming in, you're doing multiple inferences, repeatedly carrying out a lot of the same computation. Okay? There are going to be lots of opportunities to try and not repeat this computation, just like in the normal searches and so on, caching, you don't have to do all that repeated searches. So one of the clever young minds, or could be an old mind too, but the young mind's more likely to come up with clever techniques. This is your application. How do I'm doing the, it's repeated computation in the same query and repeated computation across multiple. How do I do it efficiently? Come up with a way to do that.
Thank you, Guri. Anybody else? Carol, you had these beautiful glasses over there earlier on the screen.
Yeah, I guess AI is the elephant in the room. I can talk a little bit about what's so interesting about these machine learning workloads. I think on the training side of things, scalability, I think, is where more investments can come in. And the scale of machine learning model training is quite different as compared to any other applications that our industry has built systems for. And I also felt like from inference perspective, it's quite interesting because a lot of these inference comes with real-time target. And what that means is, and this is actually something that computer architecture community is really good at. Let me give a few examples. In large language model inference optimization, to push down the latency, I guess there are works that talks about how to split the prefill phase from decoding phase. Split-wise, the work from Microsoft and Illinois has looked into how to split memory-intensive phase from compute-intensive phase in order to reduce the latency by leveraging disaggregation. Another great example would be speculative decoding. I guess in our pipeline computer architecture, we learn about how to separate computations and have leverage speculation using smaller models to boost the latency requirements, and then lean on the monolithic larger models to do verification to provide the correct results. These kind of concepts is actually making their ways into inference optimization. And I felt like there are many of these computer architecture principles that are being applied to improve the efficiency and performance of inference workloads, for example. And this is also why I'm quite optimistic about where computer architecture innovations can come in, even for these emergent applications that we are seeing that's being deployed at scale.
Thank you, Carol. Anybody else cares? Hiro, and then, sorry, Norm. Hiro, go ahead, and then Norm may want to. Okay.
Thank you very much. So I think emerging application, one of the most important is AI robots. And currently, human-type AI robots make boxing, and evolution is very quick. And problem we should solve is the same as Professor Hinton and Professor Benjo. Maybe that kind of AI evolve, make a copy and learn by themselves and think about harmful to the human beings. So I think computer architects should think about how to protect that kind of harmful for human being AI evolution. How we can protect that kind of situation. That is very important for sustainability, I think.
Thank you. It looks like Wen-Mei is ready to add to this.
Yeah.
You want to use this one? It's dying.
Okay, yeah, so Norm and I were just talking about this today, and building on what Carole-Jean was saying, latency has been one of the things that we assume that we will have to live with and doesn't matter. So for example, when we do let's say when we want to get a bunch of data, we would get the CPU to do the service, and that's a latency because the GPU needs to somehow synchronize with the CPU, and then the CPU needs to launch something, and then they came back and they will need to launch another kernel, and here we go. And communication-wise, we do the same thing with the network interfaces. So one of the interesting problems that we're beginning to see is that for disaggregated inference, because we need to have so many compute nodes to do the large language model inference today, that latency actually matters. So suddenly we expose a lot of these latencies that we were able to hide in the past when we're doing training. So that's why, if I have to put my finger on one thing that is going to, to make a big difference between what we're seeing in the next few years versus what we have been seeing in the past 5 years, is that we're going to see all kinds of rethinking about how we organize the system and how do we eliminate unnecessary latencies. And in some cases, I think I heard this consistency domain, we have exactly the same, we see exactly the same problem. When we need to do some kind of memory consistency, whenever we need to use a bigger domain, such as a whole GPU domain versus what we call the streaming multiprocessor domain, the latency translates into throughput. And we see that we have much lower throughput in some of the cases, especially when we try to use things across GPUs. So that in itself, if I have to put my finger on one thing that is different, it's going to be how we think about latency throughput trade-offs in the near future.
Thank you, Wen-Mei. Let's move on to the next one. So the next question is, what is the most critical innovation needed to overcome limitations? And I think, Carol, you prepared some slides there. Shall we move to those?
I'm happy to be the first one jumping into it. I guess building on top of the data that we have seen and also the conversation here, I think Wen-Mei, Norm, and panelists here have commented on. I think one of the very important critical investments that our community should look into is how do we redesign and make our software systems to be more flexible and more fault tolerant so it can adapt to changes. For example, when failures happen in large scale model training, how should we quickly react to these training failures? And once we start building these flexibility features into large scale software systems, then next slide, please. We can use these new system capabilities to also adapt to, for example, availabilities of energy. And then taking a step even further, we can then have the system capabilities to react to carbon intensity of energy or different carbon intensity of energy. And this is just a new directions that I believe our community is starting to look into, and this is quite exciting. Next slide, please. Secondly, I think as what we started talking about in this panel, there is this concept of life cycle emission, which include both operational and embodied carbon. When we started looking into this problem in 2020-ish timeframe, quantifying carbon emissions is at a very early stage. I think our computer architecture community knows how to quantify performance quite well, how to quantify power and energy with early tools like watch. But our community doesn't yet have the tool to quantify, for example, manufacturing emissions. And so first step is to, for us to understand the design space a little bit. We started building tools. ACT, for example, architecture carbon modeling tool is our first attempt to build a tool for embodied carbon quantification. And subsequently, we have also worked on a variety of different carbon frameworks for data center design space. And then we started looking into how to embed carbon into model architecture and hardware design process. For example, our CAD transformer work captures that. So what's really exciting is that some of this work is influencing Meta's internal data pipeline design for embodied carbon quantification. And then if we go back to, I think, 3 slides before, okay, there was a slide.
Doesn't seem to be here. So.
A couple more.
No, there's no more. So somehow they might be invisible or something. I don't know. We'll have to speak without that slide.
Okay, sounds good. It was quite exciting to see also carbon quantification work to start becoming available by companies like Microsoft, where they publish a sustainable cloud technology paper that looks into what is the sustainability implications of latest cooling technology. Google has most recently looked at carbon efficiency analysis for generations of TPU, for example, and they look into life cycle emissions. And just as of last week or 2 weeks ago, I guess NVIDIA published one of the first embodied carbon analysis for their H100 GPU systems. And I think quantifying embodied carbon is really complex and hard. And I'm really glad to see industry taking the very first step to make data available.
Okay, anybody else wishes to comment on the question of what kind of innovation is required? Hironori, you can let it go, I'll navigate. That's fine. Go ahead, Norm.
Yeah, I was just going to say that agree with Carol's comments. Embodied carbon can be hard to measure because if you get something from a supplier, it might be, confidential to that supplier exactly how much energy they use to smelt the aluminum or whatever it is. So you have to kind of make best estimates in some cases. But yeah, the more that we can make this a kind of an industry standard analysis and tool, kind of like Watch was. I know that's from academia versus industry, but I think that would be really healthy.
Okay, anybody else, or shall we move to the next question? So the next question is, who will deliver this innovation? Academia, industry, community, governments? Yale brought that up question, or you were asked that question by one of the audience. Any more comments? We have here people who work with government, people who work in academia, who work in industry. What is your perspective? Go ahead, Hironori.
Yale, you want to say something?
Not really.
Go ahead, Hironori.
Okay, thank you very much. So, who deliver innovation? It's naturally young generation of researchers, including a PhD student, and it means PhD student, professors, academia, and also with industry and the startups. Maybe startups will be strong innovators. This is a successful model of Silicon Valley, but I believe that kind of approach is the most promising approach.
Go ahead, Guri.
So I strongly believe the innovation will be delivered by academia. Industry can really do a fantastic job in building products and really, getting things done at scale. Academics are supposed to come up with innovative ideas. So I want to take off Wen-Mei mentioned in 2012 the GPUs came over and took over neural nets and so on like that. Well, actually, yes, that's true. But before that, in 2009, there was a class taught by my student Andreas Mushovas at Toronto, and there was a class project in that class by a student named Alex Kraszewski. And that class project was doing the first layer of the neural network on a GPU to see if it could be done. And the class project reports were online for a while. They seem to have gone off. And the conclusion of that report was just 2 words: it works. Okay? And so that came out of academia, and that then led to the AlexNet, which then led to everyone taking off. So it can be done by a graduate student in a class project, the innovation, okay? And this is, in my view, it's going to come out of academia, one of you.
What do
It's
our
going
colleagues...
to have to come from a graduate student because most of the faculty are too busy trying to satisfy the funding agencies with the BS that those funding agencies wish to fund. So Guri has a point. I think that it's going to be a collaboration, a meaningful collaboration. And academia, so why do so many professors waste their lives chasing the funding agencies' demands? Well, I don't know, you can come up with your own answer. I think it's going to change when we actually invest in companies funding among the studies that the passionate graduate student wants to pursue. And my last point on the matter is the word I just emphasized, which is passion. The last question, which we didn't answer, was what advice would you give to a young architect? The advice I'd give is do what is your passion. Do what it is that you want to do. There will be a job out there. Don't chase something just because, well, I need a job. Passion. If you don't chase passion, you will have a very long, tiring career. If you do chase passion, then you'll have, whether it's long or short, I don't know, but it'll be a much more exciting career.
What do my esteemed panelists from industry think? Do you agree with what our three colleagues from academia stated?
You make it out like a Family Feud kind of thing, Dan. Three versus three.
There was lack of controversy, so.
Yeah, the problem is that, you know, some of the longest research horizon things are just beyond the time scale of industry, and that's always been the case. So that's why government funding is also important for those long time scale things that pay off in decades. The last Turing Award was for RL, reinforcement learning, and it was funded something like 30 years ago. And it took that long. And so a lot of companies don't exist after 30 years. So that's a disincentive there. But for near term things, yeah, I think it's great to have a partnership. And I think besides the funding, it's a lot easier, I know. We were talking a little bit earlier about Joel Emmer. I don't know if he's in the audience, but you know, working with students, encouraging them to have a passion, excel, do good research. I think that's one of the biggest benefits, actually more than the money, although I'm sure the academic side might disagree with me. But I think for the students, the mentoring and helping them to find good problems is very important.
Wen-Mei, you were going to avoid any controversy, or?
I will probably regret this. So I'm not speaking for NVIDIA, I'm speaking for myself here. So my prediction is that most of the innovation will probably come from startup kind of arrangements. Unfortunately, the academia funding is going through some really, really bad trends. So I really doubt that funding-wise, I still remember when I was a grad student, Yale would go to DARPA and then report something that they would like to hear, and then we will do what we want to do. And so that was a great time. And 20, 30 years later, is that, oh yeah, these people did good work. But I think Yale, being I don't think he can even hear this. So Yale being an advisor that allowed the students to do some of the things that the government really didn't explicitly try to fund. That was an amazing arrangement for his students. And so if I have to predict what's going to happen in the next decade, I think it will be more than, I would say even more important than now, that the grad students probably need to begin to think about things more along the lines of what Alex and so on, his colleagues did for the AlexNet. That is, I doubt that they published something like an ISCA paper out of that project. Okay, I really doubt it. But they won the ImageNet competition. For many universities here, the ImageNet competition may not even be on the radar screen of academic in progress. That's maybe a distraction, okay, for many of the professors. But if we're thinking about what we're going to be facing in the next decade, that kind of approach may be what's necessary, and forming startups to really carry through some of these things may be the way to circumvent some of the bad funding trends. But we will see how things go.
Thank you, Wen-Mei. Carole, you want to close this before we go to the last question and then move to audience?
Yeah, I have something that I want to sort of complement what Guri mentioned and also what Wen-Mei mentioned. I think even before the LX9 moment, there was already significant investments into GPUs, how to enable the general purpose computing stack for GPUs, and that was like something that was invested for many years by NVIDIA. But before that, there was all the additional research investments at Stanford on streaming processors, on Brooks programming language. And I think all of that investments in research seeded CUDA, GPU, and then bring us the deep learning revolution. And that's like something that's really important to think about the whole life cycle of research and the industry impact beyond that. To what Wen-Mei mentioned on innovations coming from startup, I do think that it is valuable for PhD students, for example, to spend some time, like internships, 3-6 months in industry, just to take a look at what kind of emergent applications that industry is building product for example. And then if that seems interesting, give you inspirations, then that's also something that you can leverage the longer runway at academic environment to have a deeper studies. And I think that combinations of different environment is really beneficial.
Thank you, Carole. I think
one more thing. The GPU, I do want to mention one person on this panel. He and David Kirk, Wen-Mei and David Kirk, would go around teaching classes on CUDA programming, getting universities to go programming about CUDA and about GPUs. So they also deserve a lot of credit for creating this.
Yeah, congratulations. Okay, so we thank you, Guri, for giving compliments to our esteemed panelists. We came to the last question, and that is, any advice for young computer architects? And we're going to do it in the following manner. Please be concise to leave questions for audience. We start from here and at the end. Wen-Mei, less than a minute, please. What is your advice?
Build, build, build. Think about how you can change the world by building and evaluating, not just observation. It's easy to simulate something, it's easy to imagine something, but until you build it, until you test it, until you evaluate it, you're not going to change the world by just doing simulation. It's going to be a longer road, but in the end, you'll be happier.
Thank you. Norm?
Yeah, just following up on that, I think that's similar to learning about the technologies and getting firsthand experience that I talked about earlier. And I know, we built, when I was a grad student, we built the MIPS chip. I did a lot of the layout myself. And so I learned a lot that way. And so I recommend that. It does take a little longer, but it's worth it.
2-0 for building. Hironori?
Thank you very much. So my advice is one word: never give up. So in my experience, every time first data was very bad, and sometimes disappointment. We have a data. Sometimes students have disappointed, and sometimes give up that kind of research. But every time failures, but think about how to solve, and repeatedly try the new solution. Finally, there are very good data come. So if we give up in the middle, nothing happened. But continue their dream and their target continues. Finally, we have a very good result. So for 40 years, I have never bad result. Every time, finally, good results came. So never give up. It's the most important, I think.
Thank you, Hironori. Yale?
So I've already answered that question.
Okay.
Follow
Guri?
your passion.
Do not try to solve problems that industry considers are important at that time, because by time you'll get around to potentially come up with a solution, that problem will not be a problem and something else will be.
Thank you, Guri. Carole?
Work on important problems and persist on it, and help others, enable others to build on top of your solution. And remember that publishing paper is only the first %. There's a whole 9 yards that comes after that. And so thinking about how to focus on solving impactful problems and then think about how to let others to build on top of your solutions is quite impactful.
Thank you very much, everyone. And we came to the point where we're accepting questions from the audience.